Hey guys, welcome to another video. So today we continue the journey on the topic of projectile motion. So if you haven't seen last video on projectile motions, please watch that before this one because today we're going to continue on with applying projectiles, but with vectors. So for those that don't know about the old syllabus, so projectiles has always been part of the 3-unit syllabus. Um, so with the introduction in the new syllabus of vectors, we now do projectiles with vectors. So interestingly, in the new syllabus, or the syllabus, as some of you now know it, not new, it is the syllabus. It's part of the vectors topic, right? Application of vectors, projectile motions. But previously, it had no vectors. But what you'll see today is that the formulas, the type of examples that you'll see, exactly the same. Right, very similar. Just in fact, it's probably nicer with vectors because all the formulae are captured within one formula. So let's get started. So now, can I just say, projectile motions, like I said in the last video, is commonly considered to be one of the hardest topics in the 3-unit. It's probably up there in terms of difficulty with binomial theorem and differential equations, especially with the application stuff. So this isn't meant to be easy, but at the same time, it's not, or at least this week and last week's videos, it's not meant to be that hard. The next one, though, I will try to do harder examples with projectiles, which effectively quite long. Each question is quite long, and I'll try to get past paper questions to illustrate that. So, projectile motion, and let's say with vectors. So the best way to begin this lesson is basically to start where we ended off last time. So the equations of motion, there are 6. And this is important to begin here because you'll see that there really isn't new formulae as part when we do it with vectors. It's very similar to what we did before. So we have acceleration horizontally of 0. We have horizontal initial velocity of u, which is the diagonal vector for initial velocity cos theta. And we have displacement of u cos theta t, right? So integrate, sub in your initial conditions. And then we have vertically, starts off with negative gravity, no air resistance. Now, if you're keen for an air resistance video, please go see my 4-unit, which reminds me, please, if you haven't already done so, subscribe to the channel, like the video. It just helps, with searchability, just when someone's trying to look for videos like this. So integrate this plus u sine theta. And then if you integrate that to get the displacement, squared plus u sine theta t now, and I did this last time, I'm just gonna put in red, plus height. So that height represents that if you had initial vertical height or negative height, right? If you're below like a sand bunker trying to hit a golf swing, that's what that h is. So these formulae, we did exactly the same last time. Now, when it comes to vectors, the only thing that changes is this, right? So you can see that this guy here, this guy here, this guy here is combined when we look at vectors. So let me just confirm. So the letters that are used, so obviously they call this the acceleration vector. This is the velocity vector, and this is the displacement vector. Sometimes it's S, sometimes it's R. Let's use R. I think R is the most common one. So all they do, right, when they combine it in vector form, is that they basically say this is horizontal, this is vertical. So they basically use I and J as vertical, and then all they do is put the numbers in front. So 0 in front of the horizontal, and the minus G in front of the vertical. That's it. Right. So it's actually quite neat that they basically combine both horizontal and vertical into the same formula, right? So once again, so for velocity, you have u cos theta I squiggle, right? And then plus, and maybe here, I'll put in brackets here, minus gt plus u sine theta j squiggle. You know? So not too different. In fact, it gives pretty neat questions because they can just give you V or give you A, give you R quite simply, while previously they had to give you two sets of parametric equations. So R, so that's a V and that's R. It will be U cos theta T I plus minus GT squared on 2 plus U sine theta T. And then once again, I will use a red to illustrate that there can be formulae with H and then J. There, squiggle that. So that's it, right? So you got 3 exact replicas of the formula, right? All you got to do is combine them. Yeah, what we had previously in the blue, we now combine it in the green. Now, before I begin some of the questions, then, just to recall what we did last week, also, right? So other formulae. Right. These ones here are derivable and should be derivable in question. So just make sure you have. So we have the Cartesian equation, right? So when you basically solve the parametric equation for t, you get y equals to minus g x squared on 2 u squared bracket 1 plus tan squared theta plus tan theta x, and once again, if we need it, plus h, right? If we need it. And then, you know, the next 3 are not normally given. Once again, they are generally derived, but if you had to go total time of flight, so capital T equals to 2. Now, just be careful with the 3 formulae I'm going to do now, because each of them, I think I mentioned this last time, are subtly different. So horizontal range. So you got R equals to, now subtle, right? U squared sine double angle on G. See, there's 2's and U's and thetas and G's everywhere. And max height. So U squared sine squared now. So you got sine theta, sine 2 theta, sine squared, all very similar, and then 2G on the bottom. Right. So these formulae here are derivable, but keep in mind that it'd be good if you memorize these, right? So that you know when you derive it, this is what you're expecting to see, right? I always tell my students that. So let's do some examples, right? So I'll give you a very simple one, then maybe we'll hit up 2 past paper questions just to really give you that, real life experience, right? Real world experience, not real world, but basically what they ask you in exam. So first example. Now, excuse the language, excuse the English. I try to strip out a lot of the English and just give you the maths, right? So a ball's trajectory, so trajectory path, is given by maybe I'll go the vector, 20 ti plus. So in these questions where they give you the vector, it's pretty neat because they don't actually need to give you, the angle is this and the initial velocity is. They just give you the equation, right? It's pretty just straightforward off the bat, right? There it is, right? And then they ask you stuff. So I said this last lesson, and I'll say it again. Projectile motion is actually quite easy when there's numbers involved. 20. When there's numbers, pretty easy. Next week or next lesson, when you see the videos without numbers, so where it's pure proof, right, where all the 20s and stuff are replaced with constants, right, letters. That's when the question gets a bit harder. So find the vectors v and A, right? So I'll just write that. I won't describe it. Normally, if this was a better, well, worded question, I'll say find the velocity vector, find the acceleration vector, but let's just do that. So find, let's do our three classics. Find when the ball hits or returns, maybe it's better, to the ground. Horizontal distance traveled max height, right? Just to demonstrate the point that it is exactly the same as what we did last time, right? So in this question, part A, right? I have, remember, if I start with displacement, to get to velocity and acceleration, I basically differentiate, right? I love drawing this diagram for my students. Yeah, because if you were given the other way around, you would integrate twice, right? There's a visual representation of the connection between the three. So I've got displacement. Can I ask a favor? And that favor is for all of these, I'm just going to skip the squiggle on the I and J until the end, if that's okay. Yeah, and maybe the R as well. So this is cool because I'm going to be differentiating, right, the elements within X and Y at the same time, right? It just makes life a bit easier to differentiate that with respect to time. That's velocity is 20 I plus, differentiate that, 20 minus the 10, 2 comes down 10t, 25 goes away, that's a J. All right, that's my answer for velocity, pretty straightforward. And then once again, acceleration, all right? I'll put in a squiggle there because that's my answer. So differentiate a constant, right? That goes away. So theoretically, you don't even need to write zero I at all. You just leave it out. That's minus 10J, right? For our purpose, I'm just going to write it, right? You don't need that. That's cool. Guys, that's my answer, right? Pretty straightforward, simple. Just differentiate twice. Yeah, differentiate twice. Now, you can derive these, but you and I, let's save some time. We've done this last. If you've forgotten how to derive it, see last video when the ball hits the ground. So basically, if you were to do this, you basically set the Y element to 0. In other words, this guy here, and then you solve that quadratic, right? Now I know, you know what? I'm just gonna go back here. Let's cut and paste these formulae here so I can work off that. Just move it up to the side, right? So I can just have a quick gander every time. So I want total time of flight for part A. So that's just equals to 2u. Yeah. Now, actually, these formulas, I don't even need the formulas because I don't actually have the 2u's and stuff. So instead, you know what, I'll have to do it from scratch. So let's solve this guy equal to 0. Yeah. So you can use the formulae if the question actually goes like last time where they give you G, give you U, etc. But for this one, they don't actually give it to you. So we can actually back solve it, but let's just solve the quadratic, right? Pretty simple. Divide everything by 5. Let's make this positive as well. So divide everything by -5. Look at that, it's nicely factorizable, is it? Yes, beautiful. So you know what, I don't want to squash this down here. So I'm just gonna move this over here, that's okay. Yeah, not a fan of, well, for students in my class, you'll be used to me running out of space all the time. But you know, for this YouTube video, let's just be a bit more planned about this. So I've got 5 and -1. So it looks like I've got 2 times where it hits the ground, right? Which is possible if you sort of begin with some sort of height. Yeah, so as in like if you sort of picture, if I began like on a height there, right? So when t equals to 5, it'll land on the ground, but also because that's times 0. If I went -1, it'll hit the ground as well, but I don't want that, right? So I just want this. So my answer is therefore t equals to 5 seconds. Yeah, that makes sense for part 1. So when they give you the formula, instead of using those 3 hack formulas of max height, total time, and horizontal range, we just solve it, right? Same deal. In fact, nicer, right? Because they gave me a quadratic to solve. So horizontal distance traveled. So basically, once you get total time of flight, yeah, I'm going to sub t equals to 5 into my horizontal. X equals 20t, right? So I can see the 20t being x there. So just to be clear, that guy there is x, that guy there is y. Yep. So then I know it's going to be x equals to 20 times 500 meters. Pretty easy, right? Nothing too hard about that so far. In fact, it's very similar to last week, only done slightly differently, right? That might confuse people if they don't see the connection to last week, but it's basically last week with cleaner mass, right? Which is always nice. Max height. So max height, I know I can do vertical velocity is 0. Yeah, that's when it could. So you can sort of see in this diagram that at the top here, vertical velocity is 0. So you find the time when that happens, and then you sub that time into vertical displacement. So where's my v dot? That's this guy, right? This guy here. So this guy here, right? 20 minus 10t equals 0. 20 minus 10t equals 0. 20 equals to 10t, t equals to 2 seconds. So at 2 seconds, it reaches max height. So then sub t equals to 2 into my y displacement, which is 20t minus 5t squared plus 25, right? So then you get y equals to 22. Yeah, 22 minus 5t. Oop, not t now. That's 2 squared plus 25. Now punch in the calculator. Also, that's like 40 minus 5 times 20 plus 25. 45. Yeah. So hopefully that was a good demonstration of. Let me move this. Nope, it's fine. Good demonstration of what the questions look like with vectors, right? Exactly the same types of calculations where max height and all that, you do the same thing, right? Only you shouldn't use the formulas because they don't have u, g, and theta clearly calculated for you. So let's just use the formulas that we're given. Makes life a bit easier actually because it's nice quadratics and stuff like that. Cool. If that makes sense, let's do a past paper question. So I've got one actually copied down here. I've got 2. This is from last year's CSSA paper, and it's got 4 marks, right? In 3 in a paper, 4 marks out of 70. That's like 6% of the test. 1 question, and it's not too bad. So let's read this. So Jerry stands at the top of the building, 30 meters tall. So he's got initial height. Throws a ball with velocity. Throws a ball. Velocity of that 45 degrees into the horizontal. So actually launches off with height. Ball eventually reaches the ground. Perfect. Okay, cool. Now, so with this, there's a number of things that are given, right? So, and by that I mean, let's just dig through. So that's got initial height, right? That's my h, the red h, right, in the formula. So initial velocity there, that's u. 45 degrees, that's theta. Pardon me. Derive, now what am I doing actually? Derive the vertical displacement. So vector displacement in the form of, they use S in this case, okay, we'll use this as well. Given that gravity, right? They gave me gravity as well, that's nice. Right? That's G. And then find total time, perfect. So it feels like to derive the vector displacement, they're asking you to find equations of motion, yeah, but let's do it in vectors form to save us a bit of time. So save us a bit of time. We know the acceleration vector is given to be 0I minus, in this case, gravity is 10, so 10J, right? Everything starts here, right? Everything starts with acceleration when you're deriving the equations of motion. Integrate twice. Now, before I do it, right, I know when I integrate, I need constants, right? Constants can be found when I let t equal 0. So based on all this information, right, if I was to sort of whip up a quick diagram just to illustrate what this sort of looks like. So you have some sort of height. What's important is at t equals 0, when t equals 0, right, what do I know? I know that initial horizontal displacement is 0, but I know that initial vertical displacement is 30 meters. Yeah. I also know that initial velocity diagonally is 15. It's at 45 degrees, which means this one here is going to be 15 sine 45. And this one's 15 cos 45. So both the same because cos and sine 45 are the same. So I know that this guy would be 15 root 2 on 2. And same with this guy, right? As an exact value. This is good because I'm going to be needing this green information to integrate, right? And find my constant. So remember, acceleration, integrate to get velocity, integrate again to get vector, displacement vector here. So velocity vector, I'm going to integrate 0I minus 10j with respect to time. Just keeping in mind that what I'm really integrating is this bit, right? The I and j are just there just to hang on for decoration, right? So let's see. So when I integrate this, integrating 0 gets me, now I'll put constant 1 minus 10. Well, actually, maybe I'll go plus bracket minus 10 plus constant 2 j dt. Oh, I integrated it, so the d's are gone now. Get rid of this, get rid of this. Yeah, so that's what I get. So I know that when t equals 0, right? When t equals 0, in this case, this is like x dot, right? Yeah, then c1 equals to 15 root 2 on 2. So I'm going to sub that into there. Also, when t equals 0, initial velocity is that. Yeah, oh, I forgot to integrate. I forgot to put a little t here. Yeah, that's why I was like, why is there? Shouldn't be anything left when. So when t equals 0, that's gone. Vertical velocity, so c2 is also the same thing. Root 2 on 2. Guys, I'm going to sub, just to be clear what I'm going to do, right? I'm going to sub this guy into here. I'm going to sub this guy into here to get therefore. Let's just make sure I'm not, yep, therefore. Velocity vector right now is 15. It's just a constant, yeah, just a constant. I wish they chose a nicer even number instead of 15, maybe 16, because then I'll get no fractions. But maybe they did intentionally, just make it look a bit uglier than it is to make it look a bit harder. But otherwise, it's actually not that hard. 1, 2, j, right? That was fun. That's velocity, right? Once you get velocity, let's now do it for displacement. Now they're using s for displacement, so I'm going to integrate everything here. So let's just write it again for full working out. It's not hard, right? It's just like it's just a bit tedious in writing it out over and over again. So dt, yep. So when I integrate, so s, integrate that, that's just a constant. So it becomes 15 root 2 on 2t times I. Sorry. So I'm going to show my teacher, I'm going to show your teacher that there is a plus c3 I. So every time you integrate, you got to do that plus this guy, integrate that, becomes minus 5t squared plus 15 root 2 on 2t plus c4 j, right? And I know, you know what, let me shift this up a little. No, I've got space. That's good. So when t equals 0, right? When that's 0, initial horizontal displacement is 0, right? So then C3 is 0. When t equals 0 there, initial vertical displacement is 30, right? So therefore, my displacement vector would be 15 root 2 on 2 ti, because that's 0, right? Just to be clear, I am subbing this guy into here, and I'm subbing this guy into here, right? You know what? You can do this using the old method where you split it up and then sort of write the answer finally in vectors form, but that's no fun. Let's just do it all together. Plus minus 5t squared plus 15 root 2 on 2t plus 30 for initial height. And that's my answer, guys. I mean, exactly the same as last week. If you've done it, if you saw last week's video, exactly the same, only everything's in vector form, right? That's part A, 3 marks. Right? Classic. So moving this up a bit. So, oh no, I'll do down in this space here. So find the time it takes for the ball to reach the ground. Easy, right? So when the ball hits the ground, what do I know? So part 2, when the ball hits the ground, what do I know? Vertical height is 0. So when vertical height is 0, right, I'm subbing in this bit here, right? This bit here is vertical distance, right? Sub that equals 0. So then you just have a quadratic to solve. Admittedly, a very ugly quadratic, but then you just hammer that with a quadratic formula. Right? Nothing too wow about that. So root 2 on 2 plus 30 equals 0. Get rid of negative, divide by 5, and maybe times by 2 as well. So let's see. Let's divide by negative 5 first. So t squared plus, minus, right? Minus 3 root 2 on 2. Oh, I forgot the t there. It's naughty. Right, t plus divided by minus negative 5, so minus 6 equals 0. Yep. Now, you can then punch this into the calculator like this. Sorry, use these variables for me. I like whole numbers. I'm not a fan of, well, sorry, let me say again, not whole numbers because it's said there. I like no fractions. Right? Fractions are not cool. So using the quadratic formula on this, right, I got that equals to 3 root 2 plus minus. You know what? I've done that thing again where I've squashed it. So I'm just gonna borrow some horizontal space. Perfect. So root 3 root 2 squared, which is 18, I guess, for AC over 2 times A. And I believe if you did the answer right, one of them's positive, one of them's negative. The positive one's 3.7 seconds. Yeah, 1 mark, not hard. Yeah, solving quadratic exactly. That's how you do it. 4 marks, CSSA. Not too bad. Yeah, not too bad, guys. Let's do one more. So in the Victorian syllabus has had vectors and projectiles for a while. So back in 2007, there's a question from the MAV papers that looks like this, where let's say a toy plane of mass 1.5 kilograms is projected horizontally from off a cliff. Just make sure there's no that 1.5. Where's that used? It's not used. You're just making sure there's no forces in play. Perfect. Right. Cool. I find it interesting. So in the Victorian papers, whenever they do these questions, they're always silent on gravity. So you just got to assume gravity is 9.8 all the time. Right? Just keep that in mind now. Okay. So I got mass of 1.5. Right. I don't think that's used. I don't think that's used. Or maybe it's used in a different question, which I cut off. But so projected from vertical height, vertical cliff. So initial vertical distance is 40 with a speed. That's u. Take O as the origin and T as the top of the cliff, with I directed horizontally to the right and j. Yeah, okay. Ignore air resistance. Perfect. Hey, wait. Take 0 as your origin and t as the top of the cliff. So we're at the top of the cliff right now. So you're talking like, that, right? Yeah, so there's no sort of going up and over. It's just downwards, yeah? We're on the top of the cliff and you're just going to go down, yeah? I think. Let's have a look. Yep, looks like it. There's no middle term there. Right, show the position vector of that. Okay, cool. We're going to once again derive our formulae. Find the total time taken to reach the ground and the horizontal. So this one's total time of flight and horizontal distance. So that's range, right? So time taken, that's capital T. Horizontal distance, that's capital R. And then find the Cartesian equation. Oh, nice Cartesian and sketch. Cool. All right. How many marks are there? It's like 2. I think this one was silent on the marks there. It's probably 2 marks for that one as well. So 8 marks all up. Okay, cool. All right, let's do this then. So what's not given here is gravity is 9.8. Right? But let's assume that as given. Okay, let's do part A. Yeah, part A, where we always start with the acceleration vector 0I plus minus 9.8 gravity j, right? We know vector, so velocity vector is this guy integrated, integrated, right? So we're integrating. So once again, what do I do? So maybe I do levy when t equals 0. I got x equals 0. I got y equals to how many? 40 meters, right? But I got x dot equal to 0 degrees, right? Toy plane projected horizontally, right? Projected horizontally, theta is 0, right? So what that means is horizontally, I got u cos u cos 0, so u is 5, that's just 5. Vertically, sine 0 is 0. That makes sense because if I'm just projecting horizontally, there is no initial vertical velocity, right? So I'm going to use these 4 elements to find my 4 constants, right? When I integrate, just keep that in mind, right? That's what it's much cleaner because it's horizontal. There's no initial vertical velocity, so it makes life a bit easier. So integrate 0I minus 9.8j, once again dt. Integrate now, what am I integrating? I'm integrating the constant there and I'm integrating constant there, right? So velocity equals 2. When you integrate 0, it becomes just constant 1. Integrate this guy, minus 9.8t. Actually, maybe I'll do what I do for plus minus. Yeah, let me clean it up a bit. So plus minus that, plus c2, j, and then when t equals 0, x equals 0. Yep, so not x equals 0. Let's just solve it. So c1 equals 0. And y equals to 40. That's gone. So c2 is 40. So just like before, this guy pops into there. This guy pops into there. So therefore, velocity is 0. Yep. No, wait. Yeah. Sorry, I put in the wrong number. That's a 5, right? Yeah, because initial horizontal velocity is 5, so that's 5i. Yep. And then plus this guy's not that, it's 0 actually, my bad. I subbed into displacement by accident, right? Should be subbing in velocity. Yeah, should be subbing velocity. That goes in there. Beautiful. Okay, that's better. 5 in there, and then 0 in there, which is a nice little. I don't even need the plus there, right? Let's just, oh no, let's put it as a plus with brackets because you can see that there's a plus with brackets here. So let's just maintain that structure. 9.8 T J. Yeah, that's my velocity vector, right? Apologies for that little bit of confusion. I subbed in these ones when I really should be subbing in these ones, right? Subbing the wrong ones. So let's do that for the last bit now. That is surely a typo in the question. Show the position vector that they're using A. Yeah, I think it's R. Quick look at the answers. Yep, they're using R in the answers, so they actually typed it in. So therefore R equals the integral of that. plus negative 9.8 t j dt. Once again, what am I integrating? I'm integrating constant there and a linear function there. So I know that that's going to be 5t I. So be very clear with your integral. This guy integrates plus, that's linear, so it'll be 9 minus, we'll divide that by 2, so minus 4.9 t squared plus, oh, I forgot to plus the constant. That's very naughty of me. So let's just go. Let's just delete it. Yeah, let's just be good. Plus C3 I plus negative 4.9 t squared plus C4 j. When t equals 0, initial displacement, right? X is 0, so then when that's 0, so C3 is 0 and C4 is 40 meters, right? Which gives me exactly, therefore, the R to be 5ti plus, and they've, in the question here, they've swapped it around, so 40 minus 4.9 t squared j. Perfect. Yeah, that's how you do it. So I feel like I need more paper. So what I'm going to do, I'm going to copy the questions into the next page as well. All right, done part A, proved. Now, total time taken, easy, easy peasy. So for part B, easy, but total time taken now. When total time taken, I know vertical height is 0. Yep. Sub that into this bit here. Set that to 0, right? So then I know it's actually quite a clean quadratic. Don't even need the formula. T squared equals to 40 on 4.9. T equals 2 if you did it. About 2.86 seconds. Yep. So square root obviously can't be negative, right? So if you had to do it, you just get rid of that. Square root on the calculator. Beautiful. Now, it's a double question. The horizontal distance. So sub that into the horizontal sub t equals to 2.86 into x equals to 5t, right? Sub it into there. Pretty easy. So therefore, horizontal distance travel is 5 times 2.86-ish. Maybe, you know what? Let's be more exact. 40 on 4.9. I have a calculator here. Let me just make sure that that's right. 4.9. Yeah, so times it by 5. 14 something, is it? Beautiful. 29 meters. Great. How's that? Yeah, pretty easy for part B. Part C, find the Cartesian equation. So solve it parametrically, solve the parametric equation and then sketch, right? So it's going to be some sort of. Now, so part C. Parametrically, so if I have x equals to 5t, right, and I have what's that, y equals to 40 minus 4.9t squared. Parametric parameter is t, so make t the subject. Sub this dude into that guy. Therefore, y equals to 40 minus 4.9 x on 5 squared. Therefore, y equals to 40 minus 4.9x on 25 or 6 squared. Yeah, you can leave it like that, or 49 on 250 would be fine, whatever your teacher wants, but that's your answer. Easy. So, and then the graph, they want me to graph it. So what do I know about the graph? I know that initially the vertical height is 30. This is x, this is y. So that I'm trying to sketch this formula, 30, 40. Initial. Oh, why do I keep saying 30? Well, I keep saying 30. 40. I said 30 because it looks like 30 on this. So the graph that they gave you isn't high enough. So initially it's at 40. Weird, right? And so it reaches the ground when y equals 0, 2.8, 14.29 is the horizontal distance travel. So 14.29 is there. Something like that would be your graph. Parabola. How's that? Not too bad, right? Not too bad. Hopefully, vectors with projectiles. It's very similar to vectors without, projectiles without vectors. The only difference is that it's probably cleaner in terms of the equations and the maths. You solve quadratics that are relatively simple because there's no, well, in this case it's different because they actually gave you the angle, etc. But in most other cases, he can just give you the quadratic and stuff for you to solve, and it's quite nice. All right, guys. I'm going to leave that video there. If you like that video, please subscribe, give me a like, and tell your friends. Next video is going to be on harder questions in this topic. So stay tuned for that. I'll see you guys later.